We will update.
It's live now.
Okay. I say that's the e-certificate, right? I think we wait until 4 o'clock, right, Dr. Norma? I think we will start. It's already live now. Okay, we are already on now. Okay. Assalamualaikum and very good afternoon to everyone. Welcome to the final lecture in the series of lectures under program online global classroom. My name is Amiruddin. The final lecture will be given by Dr. Bakhtiar Ul Haq, Assistant Professor from King Khalid University in Saudi. So, the topic would be introduction to the density functional theory and its application in material science, right? Um, before I invite Dr. Bakhtiar to begin his lecture, let me briefly read his biography. Dr. Bakhtiar was born in Pakistan in 1980 something, right? He obtained his degree and master from Pakistan and PhD from UTM in 2014, right? In computational material science based on DFT, right? And then Dr. Bakhtiar spent time as a postdoc in South Korea, and before he joined King Khalid University in Saudi as a full-time assistant professor. Um, Dr. Bakhtiar is very active in publication. He has over 80 journals and conference articles published, attended more than 20 conferences, um, and he also won a few awards, yeah, during his during his study. Um, so without further ado, I would call Dr. Bakhtiar to start his lecture. I also like to remind the audience, right, that if you have any question, you can post it on the top chat, and then during the lecture as well as at the end of the lecture, I would remind Dr. Bakhtiar about question, and he would probably try to answer if there's any question during the lecture, as well as at the end of the lecture. All right. So without further ado, Dr. Bakhtiar, the classroom is all yours.
Okay. Thank you, sir. Thank you so much. I will start my lecture. The title of my lecture is Introduction to Density Functional Theory and its Applications in Material Science. Here are the outlines of my lecture. Like I will say a few things about the first principles approaches. Excuse me. And their significance in material science. And then we will talk about the density functional theory. And at the end, I will present some results that we obtained in our research group. So the first principle calculations, it is also known as AP initial calculations. It is a method to calculate the physical properties of materials directly from fundamental physical quantities based on the quantum mechanics. First principle calculations don't require any parameter to adjust the results except the information about the constituent atoms, the atomic numbers. And first principle computations do not require any experimental knowledge to carry out calculations. So why we use the first principle computations? It's because the first principle computations have played a major role in understanding the physical properties of materials and challenges associated with materials in multiple applications at multiple scales and advanced technologies. These methods provide insight into the properties and processes in atoms, molecules, and condensed spaces, ranging from bulk crystals to surfaces, interfaces, and nanostructures. First principle computations has advantages, like by first principle computations, one can save precious time and raw materials. Similarly, one can understand the feasibility and characteristics of material or particular application before conducting a real experiment, resulting in reductions of trial and errors or guess work, and in return, higher chances of success. So, by first principle calculations, one can get better understanding about how and why processes or products is working, and this helps the researchers to control the molecular level behavior of the materials, which eventually influences their bulk scale behavior. Moreover, it is an important tool for supporting or complementing the experimental studies. Therefore, the first principle approaches have become an important pillar of the scientific investigations under the umbrella of the theoretical investigations. There are several first principles or ab initio methods, like Hartree-Fock method, post-Hartree-Fock method, quantum Monte Carlo method, valence bond methods, and density functional theory. Among them, the density functional has been emerged as one of the most practical and feasible tools in material science for the calculations of the physical properties of materials. So the fundamental aspects of the density functional theory is that It is a computational method that derives the physical properties of the material based on determination of the electrons. The term functional within the density function theory is defined as the function of a function. Like we have the electron density, which is the function of the x, y, and z coordinates. And then the energy is a function of density. So again, as we said, the density is a function of the position. Therefore, we can say that energy is the functional of the density, because density itself is a function of the position. X, Y, Z are the X, Y, Z are the special coordinates, are the coordinates and the Cartesian coordinate system. So DFT allows to get information about the energy and the physical and chemical properties of materials at lower cost than traditional approaches based on the wave function. Therefore, DFT has revolutionized the computational material science since the last 20 years. So the basic, DFT at a glance is that DFT is presently the most successful. DFT has become the most successful approach in computational material science for the calculation of electronic structures and the physical properties of materials. And its applicability ranges from atoms, molecules, and solids to nuclei, quantum, and classical fluids. And in its original formulation, the density functional theory provides the ground state properties of a system where the electron density plays a key role. DFT have many advantages, like it offers a very good scaling of computational cost with system size. It allows calculations to be performed on the large and complex system. And Walter Kohn, who developed the density functional theory, was awarded with the Nobel Prize for the DFT. So this has endowed the DFT with a prestige that makes it hard to criticize. So the background on the concept of DFT came up in the 1920s after the Thomson and Fermi models. And then in 1964, the Hohenberg and Kohn, they actually developed density functional theory by publishing a paper. In 1965, the Kohn-Sham turned the DFT to a practical tool by introducing their equations to the solution of the many-body problem. And then in 70s and 80s, there have been developments in terms of the new the exchange correlation functionals that helped in the accuracy and efficiency of the density functional theory. And then in 1998, the Walter Kohn were awarded with the Nobel Prize in the field of chemistry. So that's the background of density functional theory. And now, to know how density functional theory works, we step back and learn how the quantum mechanics works in explaining the properties of a material. So in quantum mechanics, to understand the behavior of a material, the Schrödinger equation is used. This is a typical Schrödinger equation where this is the wave function, which is a 3-dimensional wave function for n-particle system. And H here is the Hamiltonian, which has several components like the kinetic energy operator for nuclei, the kinetic energy operator for electrons, and we have Coulomb interactions between nuclei and electrons, and there is Coulomb interaction between electrons and electrons. and we have Coulomb interaction between nuclei and other nuclei. So this is a very complex equation because the wave function associated to an n-particle system is a 3n-dimensional wave function, because there are n particles and every single particle has a 3 degree of freedoms. Okay. So if there are n particles and every particle has 3 degrees of freedom, then the wave function becomes 3n-dimensional. And therefore, the exact solution for such a problem is impractical, even if the fastest, or even if we use the fastest available computer. To solve such a problem, the approximate methods are used. And the first level of the approximation that used in DFT was proposed by the Born-upon-Hammer. Born-upon-Hammer propose or presume that the nuclei can be treated as fixed particles because they are very heavy compared to the electrons. And since they are very heavy compared to electrons, they are moving very slowly. Therefore, the kinetic energy term and the interactions between the nuclei with other nuclei can be neglected. Hence, we left with a relatively simpler form of the Born-upon-Hammer Hamiltonian. In this Hamiltonian, the first term is the kinetic energy operator for the electrons. The second term is the kinetic energy operator of the electrons. It is the potential energy operators, or the interactions between electrons with other electrons. And then we have the term which is the external potential, is developed by the ions. So we have this form of the Born-upon-Hammer Hamiltonian. In this Hamiltonian, the first two terms are the general terms. The generals mean they are originated from electrons, and we know that electrons are indistinguishable particles. They don't provide, because they are same, so they don't provide the information of a specific system, because they are the same everywhere. So they are general terms. Where there is the external potential, which is system specific. This term gives us information about a system, like the external potential, which is generated by the nuclei or ion, where the electrons are living in that potential. So they can give us information whether the potential is produced or generated, suppose, by aluminum or iron or platinum. So we can get all the information about a system from the external potential term. So if I develop a proper Hamiltonian for this external potential term, then I can get the wave function and energy for that system. And in return, I can get behavior or properties of a system. So from this external potential term. So what density functional theory, or what Hohenberg and Kohn said, that the ground state electron density takes the role of the external potential. It means that the ground state density uniquely determines the 3n-dimensional ground state wave function and energy. So we can get all the information about a system from density functional, from the density, ground state density, as much as information that an external potential provide to us. So what the density from the Hohenberg and Kohn theorem says is that the ground state energy from Schrödinger equation is a unique function of the electron density. The density contains much information as a wave function does. That is, everything you could possibly know about an atom, molecule, or a solid from the electron density. And the concept of density functional theory with the concept of density functional theory, the 3 and spatial coordinates associated with many body system has been reduced to only 3 dimensions, because the density is a single quantity, no matter how bigger it is. It is a single quantity, and it has only 3 coordinates, or it is only 3 dimensions. So to prove the Hohenberg and Theorem equations, before that, we will talk about the electron density. We will learn about the electron density. This is a full wave which is n-dimensional, and we know that the square of the wave function gives the probability of density of finding an electron. It gives us finding one electron at R1, another electron at R2, and so on. Now, if I take integral over the square of this wave function over the all available variables, it will give me the number of electrons available in that space. What if I take the integral, if I integrate the square of the wave function over all the space except one coordinate, like I do here? I consider all the variables or all degrees of freedom, and I take integral of the wave function, the square of the wave function, except R1. So this equation will give me the electrons available at R1. So if I take integral of n of R and all the space, so this will tell me the number of electrons available in the space. And this is the electron density. And then before going to prove the Hohenberg theorem, we will study about the external potential and the electron density relationship. We prove that the contribution of external potential to the energy expectation value depends on the electron density. Now we know the Hohenberg, the Born upon Hamiltonian as this, which has the kinetic energy term, the electron-electron interactions, and the external potential terms. And if I compute the expectation value for this, I will get like this I represent here. This T represents the kinetic energy term, U represents the potential energy term, and this is the wave functions sandwiching the external potential. Now, as I said, this is the most important term, which gives us information about a specific system. So if I expand this expectation, the expectation value for external potential, I will get like this: integral over all the space, all over the integral over all the degrees of freedom, multiplied by wave function, multiplied by the external potential, and times the wave function again. Now, in this equation, the wave function are 3n-dimensional, where the external potential is only 3-dimensional. It only depends on one variable. So let me single out this the external potential with variable Rk. So I left with all variables except the Rk, and then times the wave function square. And this is actually this term is the electron density, as I said to you, as I showed in the last slide, that the square of the wave function or all the available degree of freedom gives us the electron density. So I can write this equation as V external is equal to the expectation value of the V external sandwiched by the wave function. This is equal to the external potential times the electron density. Now here we have the full wave function, which is n-dimensional wave functions, and which shows that the wave function is the functional of electron density. From this equation, we can say that the expectation value of the functional of the wave function is functional of the electron density. And that's what the Hohenberg said, that we can get as much information from the wave function by the ground state electron density. Now we will prove the Hohenberg theorem and prove that as the Hohenberg-Kohn theorem says that the ground state density uniquely determines the external potential, and consequently the wave functions and the energies, etc. So we will prove this by contradiction. We will say, let's we say that the ground state electron density does not uniquely determine the external potentials. Means that different external potential can have the same electron density. And if we suppose that, then we have we suppose two external potentials, like we have external potential 1, which has ground state wave function 1, and the density, the ground state density corresponding to this external potential, let's say it is this is the ground state density corresponding to this potential, which is N1 R. And then we have a second, we consider a second different external potential, Vx2. And the wave function.
Sorry, Dr. Bakhtiar. Can you get a bit closer to your mic? Maybe the sound not very clear to some audience.
Okay. Can you hear me now?
I think yes, I can clearly. All right. Okay. Sorry. You can continue. Yeah.
Thank you. So what we consider here, that we have to prove the Hohenberg-Kohn theorem by contradiction. We assume that there are two different external potentials, V1 and V2, that has ground state wave function psi1 and psi2, and the energy, the densities corresponding to V1 is N1, and the density corresponding to V2 is N2. And the Hohenberg and Kohn theorem says that these densities must be different. Every external potential should have its own density. But we prove this by contradiction. We say that there are two external potential that have same density. Okay. So this is the density for external potential 1, and this is the density for external potential 2, and we assume that they are the same. So I will, to prove this, I will take the expectation value of the Hamiltonian one using the its ground state wave function. Now, if I calculate the expectation value of the Hamiltonian one with its ground state wave function, I will get the minimum energy, because I use its own ground state wave function. If I use another wave function for Hamiltonian one, which is not the ground state, then I will get the higher energy than that of the using the its own wave function. So if I use wave function 2 to compute the expectation value of Hamiltonian 1, then the energy corresponding to this expectation value will be higher than that of the Hamiltonian 1 by using the ground state wave function. Okay, so this is reasonable because this is the ground state wave function for Hamiltonian 1, but this is not the ground state wave function for Hamiltonian 1. Now, I expand this Hamiltonian So if I expand this Hamiltonian, I will get like this. This is the kinetic energy, expectation value of kinetic energy term, and expectation value of potential energy term, plus the integral of the external potential and the ground state density. We just calculated this in the last slide. And then if I expand the same for this Hamiltonian, for this expectation value, then I will get like this. This is the expectation value. If I expand the Hamiltonian one by using the wave function 2. Now, I assume that the density for external potential 1 and the density for external potential 2 are the same. So this terms is the same because I assume that. So the difference is only in these two terms. So I can say that the expectation value of the kinetic energy and potential energy using the ground state or using the wave function 1 is lower than the energy of the expectation value of kinetic energy and potential energy terms using the wave function 2. So if I do the same for the Hamiltonian 2, which is associated with the second external potential. This is the Hamiltonian 2, which is the second associated with second external potential. And if I compute this expectation value by using its own wave function, then the energy will be lower than that of the Hamiltonian, the expectation value computed with the wave function of the first external potential, because this is not its own external potential. This is not its own wave function. This is a different wave function. Therefore, the energy of this expectation value will be larger than the energy of the this term. Okay. So again, like this, I can write that the total energy for the expectation value of the kinetic energy and potential energy using the wave function 1 is larger than the the energy corresponding to the expectation value of kinetic energy and potential energy using the wave function 2. So I have a condition like this now. At first, I said that the kinetic energy and potential energy, the expectation value of kinetic energy and potential energy using wave function 1 is smaller than that of the expectation value of kinetic energy and potential energy by using wave function 2. But in the second term, I say that the expectation value of the kinetic energy and potential energy by using wave function 1 is larger than the expectation value of the kinetic energy and potential energy by using wave function 2. So this cannot be true at the same time. Okay, so this is absurd situation. This means that by considering the same density functional theory, by considering the same electronic density for different external potential is absurd. Two different potentials cannot lead to identical ground state densities. Every external potential has its own ground state ground state density. Therefore, the ground state density uniquely determines the external potential and consequently the wave function and energies, etc. So in summary, the Hohenberg and Kohn says that the Hohenberg and Kohn theorem says that the ground state wave function is functional of the ground state electron density, such that the ground state density can be given by this equation, the square of the function times the variables, all the available variables in the space. And similarly, we can also, in the follow-up, we can say that the electron, the energy is also a function of the ground state density. So we can show this variational property that the electronic density that minimize the energy functional is the ground state density. This means that if we use, because energy is functional of the electronic density, so if we use the ground state electronic density, then the energy will be minimum than if we use any other electronic density, because energy is functional of the electronic density, the ground state electronic density. So now we have these relations that the energy is density, or energy is a function of the electronic density, but we don't know how to solve this equation. And it was the Cohen-Sham equations that solve this problem. In the Cohen-Sham equations, the many body energy is shown in the components form. Like we have the kinetic energy term for the single particle system. Then there is the potential energy. We have the external potential, and then there is the exchange correlational energy. This term is the kinetic energy for single particle system. We have electron potential energy, the external potential due to nucleus, and then we have the exchange and correlation energy term. Exchange and correlation energy shown here is the function of the electron density that gives all the contributions of exchange and correlation to the total energy. So we have, this is the Cohen-Sham energy functional. And this can be solved by using this Hamiltonian for the energy. So here, they present a solution for this many body problem. But still, the problem exists is the solution of the exchange correlation energy. So to solve this, several exchange correlation functional has been presented, and the most popular one is the local density approximations, which assumes that the electron density is varying, and hence the inhomogeneous density of a solid or molecule can calculate it using homogeneous electron gas. So
okay, sorry, Dr. Bakhtiar.
Yes, sir.
Can I ask back one? Can you go back one slide about Cohen-Sham equation? Just one slide back. The Cohen-Sham equation is now. No, the Cohen-Sham equation, I think before this slide, right? Yes. So yes. Okay. So this is the wave function here is for single particle. It's not for many particle wave function.
Yeah, this is a single particle. This is single particle wave function.
All right. Okay. Which is much easier to solve. Is it right?
Yeah, it is much easier to solve compared to the n particles system wave function.
All right. Okay.
So the LDA assumes the electron density is varying slowly, and hence the inhomogeneous density of solid or molecules can be calculated using the homogeneous electron gas. So the exchange correlation energy is split into two components. One is the exchange term, And this can be calculated exactly by using this formula. Whereas the correlation, for the correlation terms, no analytical solution is available, but the Bernie-Adler and David Sipperle performed some very heavy quantum Monte Carlo simulations, and they derived some numerical values for the correlation term. Hence, the LDA works properly for in the case in the case of the homogeneous electron gas, but LDA face problems in the case of materials where the strongly localized and correlated electrons such as oxide or transition metals and rare earth elements or compounds exist. So to overcome the difficulty of low density approximations, and the cases where there are gradients in the electron density, where the electron density is not homogeneous, the generalized gradient approximation were proposed, which where a gradient term is introduced. So this gradient terms sufficiently solve the issue of the local density approximation, where there are abrupt changes occur in the electronic density. So with the passage of times, many developments have been done in terms of the exchange correlation functional, like LYP were produced, and TLYP, and many other hybrid exchange correlation functions have been proposed recently that produce very accurate results for the physical properties of materials using the density functional theory. Now, what we said here is that the Schrodinger equations based on the wave function and particle wave function has been transformed to the Kohn-Sham equations within the density functional theory, which is single particle Kohn-Sham equations. And there are many methods available to solve the Kohn-Sham equations, like the PWO, the PAW, and grid-based approaches. So we will talk about the LFPW approach, which is one of the most accurate approach for solving the Schrodinger equations. In this method, the unit cell is divided into two regions. One is the region where the atoms are occupied by the atoms, and the second region is the interstitial region, which is empty space. So the electron density and the Kohn-Sham potentials are expanded as Fourier series in the interstitial region, in the empty space, like this one and this one, and as lattice harmonic times the radial functions inside the spheres. So like this one, this is the equations inside the spheres. These are the inside the interstitial regions. So the Kohn-Sham equations are solved within this approach, the LAPW approach. The Kohn-Sham equations are solved iteratively. Like in the first step, an initial trial electron density is assumed or supposed. Then in the second step, the effective potential is generated from the starting density. Okay, and from this effective potential, by solving the Kohn-Sham equations, the wave function, single particle wave function, is generated here, and then from the single particle wave function, again, new electron density is derived in step 3. Okay, and then in step 4, this new density, electron density, is compared with the initial electron density. Now, if the new electron density is similar to that of the electron density which is used If the first, then we can say that this is the ground state electron density. But if there is a difference between the new electron density and initially used electron density, if there is a difference, then another iteration is performed in a similar way. So this iteration continues until the input density, electron density, and output electron density are the same. So once we get the same electron density for the input and for the output, then we say that this is the input density is the ground state electron density. So as we said, the density functional theory is little bit involves little bit complex calculations, but it's good that one should know about these equations, but it's not necessary. There are a few things that one should know about the density functional theory calculations to perform the density functional theory calculations, and they are called as nuts and bolts of the DFT calculation. They include the exchange correlation energy functional, which determines the level of the DFT. And then there is the choice of pseudo potential or full potential, and they affect both the accuracy and the cost of the calculation. Basis set is an important parameter one should specify the quality of the plane wave basis set. K points are also one should know about the K points that determine the accuracy of the gradient zone sampling. And then there is SCF that specifies the scheme that is to be used for the electronic minimization. And then there are the input parameters that are course specific. Different courses have different input parameters, so one should know about that. There are several codes available, popular codes that where the density functional theory calculations are performed for different types of results or for calculation for the investigation of different types of properties. In our group, we use normally the Wien2K, the Castef, the DMOL3, Siesta, and Gaussians. These codes we use. So I will present some results that we obtained with the Wien2K code. I will not explain the results, but I will just present that what we can obtain using this code. The Wien2K code, it uses the full potential linearized augmented plane wave method, which is embodied in the Wien2K code, which is one of the most accurate method for solving the Kohn-Sham single particle equations for electronic band structure. And the method is universal, that can be treat all materials and their properties from first principles. Wien2K is a good web-based graphical user interface. It has a good user interface, so one can say that it's user-friendly also. Here is the interface of the Wien2K code. So one have to, for the input, one have to specify a space group and have to give some the information about the lattice parameters and the angles, moreover the atomic numbers and atomic symbols of the material should also be provided in the input for the Wien2K calculations. So we can get many results from using this code. This is a flow chart of the Wien2K calculation, how this works. And one can get several results using the Wien2K codes. So we will start with the structural properties that we get within the DFT using the Wien2K code. So in structural properties, using the Birch-Morgan equation of states, the Wien2K results in the energy against the unit cell volume. So you can get this kinds of plots. They are obtained with the Birch-Morgan equation of states. And also you can get about the effect of pressure or you can calculate the pressure against the volume using this code. So when you have these curves, from these curves, one can calculate the lattice constants for different type of structures using these formulas. We calculated the lattice constant for Mg2 FeH6. These are the results that we calculated, and they have been found in very good agreement with that of the experiment and other theoretical results obtained using different approaches. Similarly, using the density functional theory calculations, one can study the thermodynamic and energetic stability of a material. Like here we studied the thermodynamic stability of different monolayers of germanium sulfide. Using these formulas, we calculated the cohesive energy using this formula, and we calculated the formation energy using this formula. So these two formulas are used. Beside this, one can also investigate the dynamic stability by calculating the Kohn band structure. Kohn band structures gives information about the stability. Like here is the Kohn band structures we determined for the lead sulfide, lead selenide, and lead telluride monolayers. We did not find any imaginary frequency. If any imaginary frequency occurs here, that shows that material is not stable. But since there is no imaginary frequency available in these Kohn structures, so we can say that they are dynamically stable. So similarly, so this Kohn band structure cannot be calculated directly in Wien2K, but we use the results of electronic structure that obtained from the Wien2K code, and we use it in the Phonopy code. So Phonopy code gives these results based on the results from the Wien2K code. One can also calculate the formation enthalpies for different types of materials and alloys, like we did for cadmium doped zinc oxide using this formula. This formula is used to calculate the. So what we did, we calculated the total energy for the alloy, zinc, the cadmium doped zinc oxide, and then we calculated the total energy for cadmium oxide and zinc oxide separately, and use this formula to find the formation enthalpy. Similarly, in case of the alloys, one can find the TX phase diagram, which gives the information about the solubility of different materials in an alloy at a critical temperature, different critical temperatures. In the electronic properties, we can obtain the electronic band structures, density of states, and the charge density distributions. Like here, we obtained electronic band structure for different different polymorphs or two-dimensional tin selenide. So this is the electronic structure that we obtained with TB and MBJ exchange potential, which is one of the most effective potential for calculating electronic structure that gave results near to the experiment. And beside this, one can also see the contribution of different orbitals into the electronic structure by determining the orbital result electronic band structures. Like here, we determine orbital result electronic band structure for the 10 selenide, and this is the electronic structure, the contribution of only 10 s electrons, which contribute in the valence band, especially in the valence band maximum. And this is the electronic structure contribution of the p orbital from the SN from the 10 atom, which shows that the major contribution comes from the p orbitals. And this is for the contribution for the orbital, which doesn't show any significant contribution to the electronic structure. Similarly, this is for the selenium p orbital, the electronic structure, which shows that major contribution comes from the selenium p orbitals and the valence band of the electronic structure. And even for a specific orbital, like we saw that the 10p orbitals have major contribution. So one can check the contribution in different directions, like this is the dispersion of the p orbital in the x direction. This is the dispersion of p orbital in the y direction and in the z direction. So even for one orbital in a specific direction, one can resolve the orbital resolved electronic band structure. Here is similar for the selenium, the px, py, and pz orbital. Beside this, to understand the contribution of various states into the electronic structure, one can determine the total and partial density of states corresponding to a specific band structure, like here we did for the zinc oxide, two-dimensional zinc oxide. This is the contribution from the different states. So these are the density of states one can calculate. Moreover, to check the type of bonding within a material, the chemical bonding, the electron density distribution can be calculated, which gives the nature of the bonding between the atoms within a structure. This is the contour plot for the electron density distribution. So these all information we can get about the electronic properties using the V2K code. Similarly, we can study about magnetic properties. We can calculate the magnetic momentum for different materials. Here and also the crystal field splitting energies can be calculated from the spin polarized density of state using the DFT calculations. One also can study the magnetic type of magnetic coupling at the ground state for different materials. Like here we studied for nickel doped zinc oxide, the ground state coupling, and here is the ground state coupling for the iron doped zinc oxide. These are the spin polarized density of states. One can check the arrangement of the orbitals or the states for upspin and for downspins like this. And we also can calculate optical properties by using the Kramer-Skroning equations. So in optical properties, we can determine the dielectric functions. This is the real part of the dielectric function and the imaginary part of the dielectric functions. And then we also can derive the absorption spectra from the dielectric functions using this equation. We do not use this equation. Actually, these equations are embedded in the code. So the code just gave us the results.
Okay. Sorry, Dr. Bakhtiar. I have one question just appear. Right.
Okay.
This question asking what is the main difference between the codes? You mentioned there are many different codes available in the FT calculation, and one audience is asking the difference between them.
Different codes have been designed for calculations of different properties. Like V2K is mainly for the calculation of solid crystals. Okay, so in case one wants to calculate the properties of molecules, then they can use like DMOL3 or even the Gaussians. Similarly, for the surface study of the surfaces, one can use the even the Gaussian code like this. So different codes are designed for different properties, because it's a very vast area, and in material science the people are using working in different sites. even for biological purposes, for chemical. So different codes have different applications that are designed for different materials and different properties.
Okay, can you accept one more question?
Yeah, sure, sir.
All right. Another question is the audience. One of the audience asking about thermodynamic stability. It said occurs at the lower energy state. How about highest? I think probably a highest stage or maybe a highest energy state. Okay. One more time. The question, right? Stability, thermodynamic stability occurs in the lowest energy state. How about highest stage? That's what the question asks. Probably asking what about highest energy state, if I can understand correctly from the question.
So what I got from the question that the lowest state is basically the stable state, but if we suppose increase the energy, right? So it's possible that material will go through a phase change. There will be maybe a change in the structure of the materials, and we can get different phases, or I mean different structure for same materials at different energy. What I get from this question, I believe, if I understand it correctly.
Okay, thank you.
Then this we also can obtain the reflectivity spectra for materials. Like here we obtain for the let's two-dimensional selenide, and using this equation, and then there is the refractive indices, information about refractive indices, and the loss function. The loss function gave us information about the traversing of electron in a medium. So this is the equation used for the loss function to understand the mobility of electrons within a medium. One also can investigate thermoelectric properties. For thermoelectric properties, normally we use the bootstrap code, which obtained the results from where the electronic structure results are obtained from Wien2K code, and then we use them as input for the bootstrap code, and we can get the thermoelectric properties. Like here is the electron density, the conductivity with respect to the relaxation time. We calculated this against the carrier concentration. Here is the Seebeck coefficient calculated in the bootstrap code against the against the carrier concentration. Here are the power factors against with respect to relaxation time that has been obtained from Seebeck coefficient and electronic density, like this. So these results are obtained against the carrier concentration, but one can also get results against the chemical potential. Like here, we got results for the Seebeck coefficient against the chemical potential, and here is the ZT value, which is obtained by using this equation, and this is this has been plotted against the chemical potential.
Okay, Dr. Bakhtiar.
Yep.
Sorry, you have shown at least two cases where some properties of material you have to use some additional software or package to calculate, right? Previously, you were talking
actually,
about.
Like I said, the phonon band structure is determined using the phonopy code, but the basic the input results are obtained from Wien2K code. So we use the electronic structure results, the energies that are calculated from the Wien2K code, and then we use them in the phonopy code to obtain the results for the thermodynamic stability. Similarly, for the thermoelectric properties, we use bootstrap code, But this code also, the results should be obtained either from the like Win2K codes or even the Siesta or the MASP code. So the results for the electronic structure first obtained from these codes, and then they are incorporated into the bootstrap codes to obtain the thermoelectric results.
This additional package or software, are they commercial or available?
No, they
freely?
are free. They are free actually. Not I mean they are not licensed. Like Bootstrap is free, open source, and similarly the Punapi. They have some version that are licensed based, but some of them are free. Win2K itself
Okay.
is it's not free. It has a very little cost, around 400 euros, but it's not free, open source. Win2K is not open source.
Okay. All right. Thank you.
And so similarly, we can also get thermoelectric results against the temperature. Like here, we studied the effect of temperature on the thermoelectric. So these all are the physical properties that we can obtain from using the density functional theory approaches. So in conclusion, the quantum mechanics-based density functional theory has made possible the solution of the grounds of the quantum many-body problems. DFT is based on the electron density rather than that of the wave function, which is where the electron density is three-dimensional and the wave function is 3n-dimensional. And DFT-based first principle approaches have achieved an essential position in the computational material science for designing new materials and predicting their nature and characteristics. Thank you.
All right. Okay. Thank you very much, Dr. Bakhtiar.
Thank you, sir. Thank you, sir.
I think we can spend some time or maybe Dr. Bakhtiar can spend some time to answer some question from audience. If you have any question, you can post it to top chat, right? And then Dr. Bakhtiar will try to answer that. Please, if any question. Okay, there's one question now. I can see this question asking, is this question or not? Monte Carlo methods use random sampling to estimate numerical quantities. Other model to replace Monte Carlo methods? I'm not sure whether this is a question. Can you hear me, Dr. Bakhtiar?
I can hear you.
Okay, so I repeat the question, right? Monte Carlo method, MCM, use random sampling to estimate numerical quantities. So the question is, any other model to replace MCM? I mean, Monte Carlo method, in your opinion?
I really don't know about this, sir.
Okay, and then another question is, why choose Schrödinger model to apply Kohn-Sham equation? And how about the consistency?
Actually, as I said, that and the wave function contains all the information about material. It's just like DNA of a material. And to extract that information from the wave function about a specific material, it's only the most effective way is to solve that by the Schrödinger equation. But the Schrödinger equation, because it can be solved only for a single particle or single electronic system, where there are only three coordinates or three dimensions. But if we increase the the size of the system. Like let's take example of CO2. CO2 has 22 electrons. Okay, so 22 electrons have if we multiply by 3, so it becomes 64 dimensions. So only a single CO2 carbon dioxide at molecule has 62 dimensions. So to solve the Schrodinger equation for CO2, it's impossible. That's why density functional theory says that informations that has the same information the ground quantity electron density can provide you. So this lets you free from the curse of dimensionality. The biggest problem is the dimensionality problem that makes the solution of Schrodinger equation difficult. So if we use electron density, which is only three-dimensional, no matter how much bigger the density is, it's still considered as a single quantity, and therefore it has only three dimensions. Therefore, density functional theory gave you the exact information as one can get Schrodinger equation. But Schrodinger equation solution for Schrodinger equation is very difficult. Therefore, the density functional theory make it easy, and they are consistent. Yes, because all the information available in the wave function can stand from the electron density as well.
Okay. Any other question? Actually, at the end of the question, also asking about the consistency. Again, I'm not very sure about the meaning. How
I
about the
believe
consistency?
it is. I believe, if I understand correctly, about the accuracy. I believe that the results
I
are
see.
accurate. Our experience shows that normally we got really near results or similar results with that of the experiment using the density functional theory.
Okay. Another question. How do you control the parameters? For example, or how do you control the properties? For example, electronic and magnetic properties. If I understand correctly, maybe meaning again how you control accuracy when you
Okay, so
when you calculate.
as I said to you, the basic, the input, the nuts and bolts of DFT are the selection of the proper potential, like full potential or pseudo potential, and then the basis set and the K points. You use a bigger basis set and larger K points, you can get more accurate results. The accuracy is normally dependent on the input parameters. That how we select the input parameters like K points, like basis sets, and even the selection of the potential.
Okay. Is there any other question? Yes, there's another question there. What is the weakness of ground state density model?
Okay, the weakness is that because this is the ground state, they are normally calculated at the absolute temperature. So at high temperature, or the excited state properties cannot be calculated with the ordinary density functional theory. But there is time-dependent density functional theory that gave you the information of the states properties. Even there are different codes, like exciting is a code that gave you the information about the excited state properties also.
Okay, next example, Bakhtiar, based on your experience, yeah, in order to carry out calculation using the FT, what comes first? Fully understanding fundamental or try to run the calculation first?
As I said, it's good that one should know about the fundamentals, but the main thing is as I said, one should know about the basis set, the specific basis set for their case, and the K points and selection of the potential. So if you know information about this, because they affect the accuracy or the efficiency of the calculations. So if you know about this things, so I believe it's sufficient. But it's good to know many things, but it's not necessary to know each and everything.
Okay. All right. Is there any question from the audience to the speaker? Um, okay. So far, I don't see any new question coming right from the audience. In that case, I think that's the end of the this lecture. Really hope that everyone gets something out of the lecture, and we thank again Dr. Bakhtiar for the long and nice presentation. And then and for the for the attendance, there will be a certificate for attendance, and for our lecturer, for our speaker, there will be certificate for appreciation as shown here. So on behalf of the organizer here for the program Online Global Classroom, I thank again Dr. Bakhtiar for his lecture, and I thank again everyone who attend, who watch this lecture, and really hope that this lecture will open up for new interest in computational material science using DFT. For that, I would end this session, right? And hope we will meet again in some other occasion. Thank you very much. Assalamualaikum and
Thank you,
very
sir.
good afternoon.
Thank you all for attending this session. Thank you, sir. Okay, sir. Thank you. I can leave now.
Right. I think we wait for Dr. Norma.
Uh-huh.